Yeah. Okay. So this is the second lecture, and in the first lecture I spoke a bit about the mechanics, the importance of understanding the dissipation mechanisms, improving the quality factors, and so on and so forth, and how they came back with an insight that the reservoir or the substrate is actually a very powerful medium, and suitable design of that reservoir can actually eliminate dissipation. So today I'm going to take it up one step further and say the reservoir can do a lot more things than be just considered as a source of dissipation. It can also create new kinds of interactions that you wouldn't normally have considered the system to be capable of before. And I'm going to talk about spins mostly today, and I'm also going to make the connection that measurement or measurement back action can in itself be considered as a very powerful reservoir. So the first lecture was all about mechanics. We ended up somewhere here. So today I'm going to be talking about spins in the context of cold atom spins, but the generic techniques developed by Rabi and Kassler and so on are very, very generic. And so most of these spins that have been talked about, discussed in this school are amenable to the same kinds of manipulation and control and measurement techniques. So today is going to be all about spins. And that's the motivation. So you probably encountered a whole range of different kind of spin systems, all the way from the smallest spin, the single electron, to quantum dots, NV centers. A lot of talks about NV centers, getting slightly larger larger length scales, micromagnets. And I'm going to be talking a lot about ultra-cold atomic spins, which are either in the form of lattice gases, atoms, ultra-cold atoms, which are confined in these periodic optical potentials, or indeed collective spins, which are not really confined in any kind of lattice shape, but still have a collective spin degree of freedom that we can address and manipulate, with the benefit that the collective spin have a square root of n enhancement with optical or phononic interactions, as opposed to these systems, which really are single spin systems. I'm also going to look at this, just like the first lecture, from a very AMO perspective, which is to say we have some kind of an isolated system, or a system that we are trying to isolate and look at the quantum mechanics, either single body or many body quantum mechanics of. And the very, very nice thing about ultra-cold atomic systems are that they give us isolated quantum systems with a whole number of degrees of freedom, or kind of in a sense knobs, such as the interaction strength, the strength with which these atoms interact with each other, the density of states, by which I mean the confinement, the dimensionality, the topology, and so on. These atoms are obviously they're alpha atoms, so they also have spin degrees of freedom, which I would consider internal states as opposed to motional states, and they are coupled to a reservoir. So in the ultra-cold atomic community, this last thing here, the reservoir, coupling to the reservoir, is something we all have learned to hate or try and minimize, and we have been able to do so to a very, very good degree of approximation. So the coherence, or the quantum coherence of these isolated systems can be very, very long-lived, and by that I mean minutes. What I'm going to talk about in this lecture is to basically say, in addition to all of these, and of course these are all dynamically tunable, which is an amazing opportunity to create like metastable or very novel non-equilibrium states in these ultra-cold atomic ensembles. And what I'm going to talk about is to say, in addition to all these amazing features, we also have another feature which comes about from the fact that we have amazing tools to probe or measure the various properties of these systems, which is to actually engineer or design different kinds of measurement strategies with which to probe different properties of these ultra-cold atomic systems. And these measurement strategies, I'll focus on one measurement strategy, which is just measuring the position of the atoms in a lattice, and that can be made a function of time and a function of space. And I've just denoted with some kind of obscure operator m. And the bulk of this lecture is going to be about saying we're going to prepare a very isolated gas of spins in an optical lattice, and then we're just going to subject this gas to position measurements. We're basically going to say, where are the atoms in this lattice, and what are they actually doing? And the idea is, as we try and extract more and more information, or information about the spatial distribution at a faster and faster rate, and you want to make more and more precise measurements, what is the ensuing dynamics of this lattice gas? What is the measurement back action? Okay. So measurement is obviously something, we've spoken a lot about measurement and its back action, and it's something that we take for granted for individual quanta, single atoms, single ions, single photons, and so on. And this is, we say there's all of this is encapsulated in this so-called projection postulate. You make a measurement, you collapse the system into some eigenstate rather magically, and then as you make more and more repeated measurements, there's a pretty dramatic effect of the measurement on the system being measured. We take this for granted for microscopic or nanoscale or single quantum entities. At some point, we kind of ignore the act of measurement. Okay, so in some way along the way from here to there, we say there's going to be measurement, and the measurement has absolutely no impact on the system being measured. And typically, that distinction between this and that is to basically say, well, look, this is not really an isolated quantum system. It's not a microscopic system. It's a macroscopic system, whatever that means. And measurement is a minuscule perturbation on the dynamics of the system. I'm going to approach it from a different point of view, which is to say this has very, very few degrees of freedom. This has many degrees of freedom, and is that the distinction? And if so, how can we actually engineer or design measurement strategies that take into account the many-body dynamics and use that as a feature? Okay. So I'm going to say measurement back action, while it's being seen in the microscopic domain for in the AMO community, it's also being seen for nanoscale resonators, actually first I guess by Keith in the context of electrons, and then by using photons to measure mechanical resonators in GILA and so on. But I'm going to come at it from a very many-body perspective and say, what can we actually use measurement for, and can we actually use it to generate novel quantum many-body behavior? And so this is going to be kind of my paradigm. I have an isolated quantum system, and I'm going to devise certain measurements on the system such that the back action changes the many-body properties of the case. Okay. So I'm going to take the specific example of position measurements, and the system I'm considering is a ultra-cold lattice gas, so a gas of cold atoms which have spin degrees of freedom, and they're moving around or in a very coherent fashion in an optical lattice potential. And then what do I need? I need to be able to measure the position of these various atoms, and I'm considering ensembles of millions of atoms to almost close to a billion atoms. I need to be able to measure the position. I need to be able to do so at a tunable rate, because I want to see what happens as I turn up the rate at which I am extracting information or position information from this lattice gas. And I also want it to be non-destructive. Okay, and that's a hard thing to do if you're dealing with nanokelvin atoms. Okay, the temperature scale of the atoms is far smaller than any probe that you can use to measure the position. If you're using a optical probe, which is typically what you want to do in a Heisenberg microscope sense, you shine light on it, and the scattered light extracts information about where the atom actually is. The scale of that interaction, the scale of the energy scale of the photon is an electron volt, which is about 10 orders of magnitude larger than the temperature scale of the atoms. Another energy scale would be the recoil. How much energy does the atom, how much energy is imparted to the atom when it scatters a single photon? That is on the order of a few hundred nanokelvin, but that is still, at best, compatible with the temperature scale of the atoms, but actually slightly larger than the temperature scale of the atoms. So in a sense, you can't really optically probe the position of the atoms without a significant back action. And in most cases, in the AMO community, what we usually think of is that back action has to be, is essentially trivial in the sense that it just boils the atoms out of whatever quantum state they are. It just heats it up. So it's a back action, but in a very, very trivial sense. But that won't do. We want to be able to extract position information from the atoms while keeping them, in a sense, quantum, or at least at the very, very low temperatures. Okay? And that means we don't really have, or as of earlier this year, we never actually had a tool to be able to do that. Something that simple. I'm going to measure something, but keep it in the ground state, in the quantum ground state. Okay, that actually is rather hard to do. And if you look at the kind of techniques that are out there for position measurements, or what we call imaging of cold atoms, there's something called absorption imaging. You shine light at a gas of atoms, and the atoms absorb those photons. And then you look behind and say, well, the atoms are now going to cast a shadow on the light, on the probe light. And I can use that shadow image to extract information like the temperature and the density of the atoms. Of course, you're relying on, getting a good signal relies on the fact that each atom absorbs hundreds of photons. Okay? So the energy imparter is actually very, very large. Marcus Greider's group, Emmanuel Bloch's group, and it's have developed something called a quantum gas microscope, which essentially consists of saying I have the atoms in the lattice. I don't want to release it. I want to keep the atoms in the lattice, and then I'm going to shine near-resonant laser light on these atoms such that they absorb and scatter a lot of photons. This is just fluorescence imaging. But again, the energy scale is very, very large. And so the only way the atoms are going to be pinned to the lattice is if you actually treat the atoms by imposing a very, very, very deep lattice. So that despite the energy imparted to the atoms are still frozen in place. Okay, because the trap is actually very, very deep.
But they don't go back to the same motion of thought?
No, absolutely not. They're actually heated up by many orders of magnitude. So it's an amazing technique, it's an amazing innovation, but in the context of what I'm going to talk about, it won't do.
No, the quantum state is still lost.
It's lost.
So to imagine that I just have a really deep bucket, got this cold atom,
and then my measurement process starts sort of jiggling it,
and it heats up.
And as long as the bucket is too deep, it heats up in place, in a sense. There's also techniques called phase contrast imaging, which don't use the fact, rely on the fact that the atoms not just can absorb or emit light, they can also act as a dielectric medium. They impart a phase shift of the light, but that does not involve spontaneous emission. So you're basically doing you're looking at the phase shift of the light that passes through the atoms, and you can use that to extract some very, very nice images of the spin order, or you can measure the density in a way that does not involve spontaneous emission. But at the single atom level, which is what we want to do, that those signals are extremely weak. You rely on having very dense ensembles of atoms because the dielectric constant or the refractive index scales with the density. So this won't do either. So I'm going to tell you about a technique that we developed earlier this year, after a couple of years of work, which gets past the deficiencies of each of these techniques, in that it allows us to detect the position of the atoms in an optical lattice while still keeping the atoms in the quantum ground state. Okay. And that's going to be. And then I'm going to ask the question: now that we have this novel technique, what happens when we actually use it on another cool lattice case? Okay. So to describe how this technique works, first I have to describe how we actually cool the atoms and how what techniques we use to cool the atoms and then probe them. So this is the geometry I have in mind. If the details don't matter too much, essentially what we have to say is at the end of the day we have some atoms in this egg crate-like potential. Okay, I think this is actually a very reflective surface because I always see the pointer somewhere else after it reflects off. So I have these. I think I put this too. So at the end of the day, if you do all this, bounce all these mirrors, laser beams around, you have some kind of a periodic potential in space, and the atoms kind of find their way to the minima of these potentials. Now the atoms have spin degrees of freedom, and that's going to actually become very, very important. So if I consider an atom in any one of these sites, then I can think of it as an atom or a particle in a harmonic oscillator. Okay, and so that has vibrational states or bands rather, and this is ignoring this. This is purely in the motional states or the vibrational states, but they also have spin. So really, and in the atoms we are considering have three flavors of spins because there are F equals 1 bosons. And so in the absence of a magnetic field, these three spins are degenerate, but in the presence of a magnetic field, I can move these energy scales with respect to each other. So it's very important to note that this picture here does not mean that an atom has three different lattice sites. It's just the fact that the atom, depending on its spin, has different energies within the same lattice. And I can tune these relative energies up and down with respect to each other just by changing the ambient magnetic field. Okay? And so these are the three spin states, and their energy difference is just given by the ambient magnetic field. And so at the end of the day, cooling these atoms down to the absolute ground state essentially means finding a technique that can take the atom, regardless of whichever state it is in, and then bringing it down to this lowest energy state. Okay. And note that when I cool it in that form, I'm not just reducing the kinetic energy of the atoms, I'm also optically pumping them or preparing them in a very, very pure spin state. Because there's a unique lowest energy state, which happens to be the state which has a ground vibrational band, but it's also the state that the atoms are all pumped into the m equals +1 state. Okay, So I'm optically pumping them, preparing a pure spin state, and cooling them down to the ground vibrational state at the same time. That's the technique. So the way this works is that I first tune the magnetic field such that the Zeeman energy is exactly equal to the vibrational spacing, so that, for instance, the J plus first vibrational band is in resonance with the jth vibrational band of this spin state, is in resonance with the J minus 1 vibrational band of the state. That means that now there's a degenerate coupling between these three states in each manifold. Okay? So the atom can coherently couple between those three states. Now I drive this transition on the red sideband so as to be able to get the atom from here down to there. Okay, this is just standard optomechanical cooling in a sense. And now you can see that the atom is now going to couple between this manifold, and then I can drive the red on the red line down, bring it back down there, and down some more, and then so on. And once it's there, this is a unique state because the process switches off. This state doesn't have anything else to couple to, so it's stuck. So regardless of where the atom starts out, I have a process or a recipe that can bring the atom down to this state, at which point the cooling process automatically switches off. And I managed to create a very cold and spin polarized ensemble of atoms in that state. And the way we find this out, or the way we measure this, we can measure this in one of two ways. One is the standard, what is known as time of flight imaging, where you just release the atoms from the lattice and then watch it expand. And the rate at which it expands tells you something about the temperature. And this is a time of flight expansion. Gravity points down. The atoms fall down as they expand. As they fall down, they expand. And you can look at the rate of expansion and then deduce the temperature to be on the order, say 15 to 20 microkelvin for this case. And then you switch on this Raman sideband cooling, and then you see that the same lattice gas now expands in this form, and then you deduce the temperature, it's about a few hundred nanokelvin. Okay. Yeah.
And so there's no recount stage required in the ground science cooling because it is general?
There is an optical pumping stage. I'm kind of brushing aside those details, but there is an optical pumping stage because a purely coherent process cannot remove entropy. So at some point you need some spontaneous emission. Okay, so there is an optical pumping stage. Okay. But at the end of it, you basically have very, very low temperatures. Just the temperature alone doesn't tell you is it in the ground vibrational band. Okay, it just says it's low temperature. So we can also do something that is done in the cold ion community. Maybe done in the optomechanics community. So far we don't know, like he said, there's some problems with the interpretation, but we can do sideband spectroscopy and say, we know that is the spectral distribution we expect, and in the classical regime, the red and blue sideband are essentially going to be symmetric, and as we get to the quantum regime, there's going to be a pronounced asymmetry between the red and blue sideband, and we can take this lattice gas while preserving and not release it, just preserve the atoms in the lattice and then do sideband spectroscopy. And what you see is that this is the carrier, the blue sideband, and there should be a red sideband here. It's not there. Okay. And you can use this in a sense. You can search for a red sideband here by trying to fit for one and deduce the occupancy, and the occupancy is on the order of it's limited by noise, but it's less than 0.2. Okay. And if you compare the ratio of cooling to heating rates, which would be another way of saying in steady state, what would this occupancy be? You would say based on this, it should be on the order of 0.001. Okay. So this is our state preparation at the end of this process, and as you can see, it takes all of a millisecond or so. And we have very, very high fidelities of pumping down to the ground state. 99% at least, maybe 99.9%. Good. So now we have atoms in a lattice in a pure spin state and in the ground vibrational band.
So the output field from this experiment, what then happens? Is it go directly to a photodetector,
exactly.
Or is there some heterodyning going on, or
no? It's a detect. In a sense, it's photo detection.
So, but then how do you avoid if it's photo detection, there can't be any other pumps or anything else. How do you get the frequency resolution?
So it's really a two-photon process.
Okay.
Where you basically drive. You're basically driving transitions either between the same vibrational state, or between vibration state which is increased by 1 or decreased by 1. So you have one what you call a pump field, and then you have probe field which is detuned with respect to the pump field. When the pump field and probe fields are on resonance, That's when you get the carrier, because it's just J to J transitions. And then you also, when the pump and the probe are detuned by one vibrational quanta, you have the J to J plus 1 transition. That's this. And the J to J minus 1 transition is that. And if in the ground state, then that is highly suppressed. And then at the end of the day, you don't actually do photo detection. What you actually do is you scan the probe with respect to the pump, and then you count how many atoms are left. Okay? And if you're on resonance, and you shine a very, very strong pump and probe beam, such that you have many more photons than atoms, then what you'll actually see is that if you look very closely here, there's a very small divot in the lattice gas. That's atoms disappearing, and that will only happen when you're on resonance with one of these transitions. Okay, so in a sense, it's not quite photo detection, but you're using the fact that for you to detect a transition, the atoms must have absorbed photons. And you're doing this in the absence of cooling. So if they absorb a lot of photons, they're going to get heated out. And then if you do this long enough, and then you count how many atoms are remaining, that's in a sense the same as photo detection. So we have very good state preparation, and now the question is, how do you actually use this technique for position measurements? So for position measurements, the atoms actually need to scatter photons from the into a camera. But I also told you that the technique works very, very well because the final state is something called a dark state. It does not interact with the light. Okay? So you say I have an imaging technique based on dark state. That's a contradiction in terms, because you've prepared a state that does not interact with the light, and now you want to use it for position measurements. That's mutually incompatible. So what we have to do is to somehow undo the cooling that we have done, we so carefully worked on. We have to undo it so that the atom, in a sense, is scattering photons, but in a very controlled way, and in a way that always brings the atom back to the ground state. Okay, that's a tricky part. It's very easy to take this very, very cold gas and then shine light on it so that it just boils out. That's very easy to do. But that's not what we want to do. We want to keep the atom in this ground state. But this ground state is a dark state. It does not interact with the light. Okay, so how do we do this? The way we do this is to take a coherent process by which we can take this atom up one vibrational state, at which point it couples to that state, and then we optically pump this state back to this state. In doing so, we emit one photon. Okay, and we have extracted a photon, but the atom has come back to where it started. And by doing this, running the cycle in a tunable manner, we get to extract more and more photons in a way that the final state is always the same. Okay? This process, sorry, as Pierre also pointed out, this process, if the first step here, if the first step there is induced by, say, mechanical motion, and I'll show you maybe in tomorrow's lecture how it can be induced by mechanical motion, and if it can be done so with very high fidelity, then what you have is, at the end of the day, a microwave to optical transduction. But right now I'm going to be just using this to say, look, I can run this process over and over again. Each time I run this process, the atom scatters a photon and so advertises its location to the world. So that's a position measurement. And I can do this, like I said, I can run this cycle at arbitrarily and over a very, very large dynamic range of rates. So in a sense, that's my measurement strength. How rapidly or how frequently am I extracting information about the atom's position? And I can tune this all the way from 0 to very, very large rates. And as I do that, you can see that the same lattice gas shows up with differing brightnesses, in the sense that each atom is scattering photons at a faster and faster and faster rate. Okay, so this is my measurement strength, and I can take and I can just by running the cycle more and more frequently, I can go from a point where the atoms barely advertise their location to a point where the atoms advertise their location at very, very, very fast rates. Okay, is this clear? Because this is important in what I'm going to the rest of the So this is the way we measure position. Okay. Now the question is, I'll skip this. Now the question is, now that we can measure the position of this very, very cold lattice gas while retaining the atom in the ground state, what is the measurement back action? Okay. So what is the effect of continuous position measurements on this lattice gas? And this. So this is basically this Heisenberg microscope picture. I'm going to try and measure the position by scattering photons into some lens or some camera, but that obviously has some effect on the position. And this picture is kind of a free space picture, in the sense that the atoms are in free space and they have a momentum kick and so on. But in our system, the atoms are actually in a lattice. Okay? But they can coherently tunnel around in this lattice. And the question is what happens and how do we actually detect the back action? And the way we are going to detect the back action, which in a sense is, you would say in a Heisenberg microscope picture, we are saying, I'm going to locate this atom somewhere in space. And depending on the spatial resolution, there's going to be a momentum kick imparted to it. And that's going to be reflected in the rate at which this atom tunnels around this lattice. Okay? It's a periodic potential, so it's not really free space, but it's going to tunnel around. And so the more frequently I measure the position, I expect a larger back action, and I would say that the momentum kick is going to be larger, and so I should be able to see that the atom is going to be tunneling around faster and faster. Make sense? Okay. So then the question is, how do you actually measure that tunneling rate? And what we are going to rely on is the fact that we can just watch the atoms and take a movie of this. But the atoms are moving around by microns, and there are a lot of atoms. So we need a better way of being able to look very, very locally or probe very, very locally how these atoms are moving around. And what we can do is to use the fact that the atoms, for the most cases, are just moving around without actually seeing the other atoms because the gas is sufficiently dilute. But as they move around, occasionally they're going to find a partner. There are two alkali atoms in the ground state in the same lattice site. Nothing happens, nothing strange happens. It's a perfectly stable situation. But if one of those atoms actually scatters a photon and is actually in the excited state, then an excited state atom and a ground state atom are highly reactive. Okay? And so when you have such partners and one of these atoms happens to be in the excited state, then you have something called photoassociation, a light-induced molecule formation. And what happens is that as soon as that happens, that light-induced molecule disappears. Because the energy, it's a highly exothermic reaction, and so the energy imparted to the atom by the molecule formation is far, far larger than the depth of the potential. So the atoms are just going to disappear. Okay? So that's not going to happen, and obviously it depends on light. Light is the catalyst for this reaction. The very light that we're using to measure the position is the catalyst for photoassociation. Okay? So as these atoms are tunneling around, they occasionally, if we are shining light on them, they can photoassociate. Then all I have to do is to say, as I continue doing this imaging process, how many atoms remain behind? Okay? And all I have to do is measure the total number of atoms at the end of my imaging sequence and say how many atoms are left behind. Because if the atoms are disappearing, it is because of this light-induced photoassociation or light-induced reaction or photoassociation loss, and I can relate the photoassociation loss rate, kappa, the rate at which the atoms disappear, or which is the inverse lifetime of this gas, to some terms like the filling fraction and so on, times the coherent tunneling rate. Okay, so as soon as I measure this, I can deduce for J. J is the, or to the condensed matter physicists, I guess this is called T, the Hawking term. Okay? And that's what I want to measure. How does the tunneling rate depend on the fact that I'm actually measuring the position of the atoms? And I deduce that by just looking at the stability of the lattice gas. If they're tunneling around a lot in the presence of light, they're going to photoassociate very, very rapidly, and the atoms are going to disappear. Okay? Okay. So this is kind of signifying coming back to the same picture in a kind of pictorial fashion. If I take very, very infrequent position measurements, which means I'm not shining a lot of light. Atoms are mostly in the dark. They're not revealing their position to the environment. Then what's happening is that most of the time these atoms are just tunneling around coherently. Very occasionally or very sporadically, two atoms can come to the same site in the presence of a photon, in which case these two atoms will disappear. Okay, but this happens in a very sporadic fashion. For if I'm not taking very frequent position measurements, this happens very, very rarely. And you would say the lattice lifetime tau is actually very long, because the atoms have no reason to disappear. There's hardly any light. They're not giving me any information about their position, but they're very stable. Now if I crank up the rate at which I'm extracting information about the position, I have to do that by shining more light on the system. But more light means more catalyst for photoassociative loss. So if I now increase the rate at which I'm shining light on this lattice gas, then very frequently I'm going to see this photoassociative loss. Which means that the photoassociation rate is going to go up and the lifetime of the lattice gas is going to go down. Make sense? So in a kind of another way of thinking about it, this this infrequent position measurements is a bit like this, everything's well behaved, everything's fine. But now if it starts, now the frequent measurements is like this picture in a very, very large or wide, kind of in a blizzard. The snow is performing position measurements on the cars, and the effect is obviously going to be very different. Everybody clear on the picture so far?
So you could also decrease the depth of the lattice and get the same effect, right?
We are doing this at constant lattice depth.
Right, but you could also do that instead of increasing the light. Is that right?
In the absence of the light, if I just decrease the lattice depth, there is no photo-associated loss.
Right, so you need some light, but if you want to have more transport between lattices.
Absolutely, yeah. But the idea here is that I'm going to stick to a constant lattice depth and a constant tunneling, and then the only knob I'm going to turn
is the light,
or the rate of position measurements, because I want to know what is the back action of that position measurement. Okay, so everybody clear on this picture? Okay. So our diagnostic is what is the lattice lifetime? How long do the atoms live, as a function of how fast or how frequently I'm measuring the atoms. And I expect, as I explained, that as I increase the rate of position measurements, I should go there, so I'm reflecting into that. As I increase the rate of position measurements, the lattice lifetime is going to go down, and the atoms are going to become more and more and more unstable. And in a sense, you say, well, that makes sense because I'm extracting position measurements that involves coupling the atoms to some light field, which is a source of dissipation. And so as I increase the rate of position measurements or the precision of the position measurements, I expect to see more loss. Okay. So let's do the experiment. We go from we are going to stick, like I said, to a constant lattice depth. So we know J, or the tunneling rate, in the absence of measurements really, really well, and we are going to go from sporadic measurements to very, very frequent and strong measurements, and we expect more and more photo-association, and we are going to measure the lattice gas lifetime versus the rate of position measurements.
So what are some of those frequencies? So like the trap frequency is...
Good. So the trap frequency is about, say, 20 to 30 kilohertz.
Okay.
That's the oscillation.
Mm-hmm.
The tunneling rate, no, only the black one works, right? So I have a lattice, and I can describe this by some trap depth u. And most of these are very, very conveniently found. You say, what is the typical intrinsic energy state in the problem? That is given by something called the recoil energy, which is the amount of energy absorbed by the atom upon absorption of one lattice photon. Okay, so that's a very convenient meter for me to parameterize all the energies. And so I will call this lattice parameter S, which is just the dimensionless number, which is the ratio of this. And then within the tight binding model, you can say that my tunneling rate J goes as something like the square root of S times e to the minus something like that, I think. Okay? But I mean, this is not so important, but you can say, well, if I'm tunneling from this side to that side, I expect, just from a WKB kind of an argument, that this tunneling rate is going to be exponentially dependent on this lattice depth. And that's the main term. So it's very, very important to do these experiments at a very, very low lattice depth, because you want very frequent tunneling on experimental timescales, because this tunneling rate is decreasing exponentially with the lattice rate.
So what is the typical value for J?
Yeah, good. So for the lattice depth we are at, this is on the order of anywhere a few hundred per second. Okay. But it's coherent, there's no gradient, there's no flow. It's just it's coherent, but the atoms are in a sense not going anywhere. The mean distribution is this. Okay. So that's one number. I guess that's the main important number. And the rate of measurements, the rate at which we can tune, the rate at which we can extract position measurements from the gas, we can tune that all the way from essentially 0 to about 10 to the 5. Okay, so I'm going to compare this to the rate at which we are extracting position measurements, and that can be on the order of, say, 1 to 10 to the 5. So it's a very powerful imaging technique that we have developed, because you have this very large dynamic range in the rate at which you can extract position measurements.
So that's the rate at which an atom goes through that coherent cycle.
Yeah, exactly. Okay, exactly. And then registers as a click somewhere.
Yeah, right.
Okay, any other questions? Good. So that's the experiment we are going to do. We are going to stick to a constant J and then tune this rate of position measurements up, and we say, well, that's going to come at the expense of photo-associative loss, and we can deduce the rate of tunneling by measuring the rate at which the atoms are lost. And as I explained, as we shine more and more light, to increase the rate of position measurements, I have to shine more and more light, so I expect more photo-association, and the lattice gas lifetime is going to go down. Yeah.
How is the tunneling again related to the rate of position measurement? You're saying you like reduce the tunneling by position measurement?
No. The tunneling for a given lattice step, the tunneling rate is fixed.
Yeah.
Okay. The atoms are just tunneling around.
Okay.
But as they tunnel around, they occasionally find partners. Okay. And if I have a lattice site where there are two atoms, and I shine light on that, then they can photo-associate, and both those atoms are lost. So then if I just, as a purely statistical argument, if I just say how many atoms are left over after my imaging sequence, I can, like I showed, I can relate that, just pure knowing my density of atoms and the rate of tunneling, which I know for the lattice step, I can say the rate at which I lose atoms, which is the inverse of my lattice lifetime, is related through some parameters to my tunneling rate. Okay?
So it's not into position measurements at this point.
I am doing position measurements by shining light on it, but I'm deducing the effect of those position measurements by saying,
Exactly.
how does J change?
Okay.
Okay. And the idea and the answer is, well, look, if they're tunneling around and there is no effect at all, the J is just constant, then what I really expect is that as I shine more light, the atoms are going to disappear faster. Right? And the lattice lifetime is going to go down. And the data looks like that. What's going on?
That's clearly quantitative effect.
Wow, you must be a genius.
Yeah, exactly.
Okay. So one very basic assumption failed, which is to say the act of measurements has that the rate at which the atoms tunnel have nothing to do with the rate at which we are extracting position measurements. That is not true. That is true in a classical sense. That is true when the cat is staring at a fish in a fish bowl. But that is not true in the quantum mechanical sense, because we are measuring something, we are extracting information, and that act of measurement actually has a very, very strong effect on the dynamics of the atoms. So this is an incorrect picture. That shining more light, the atoms are still tunneling around, and you shine more light, they photo-associate more. That is incorrect. A more accurate picture is, look, the atoms in the one case are indeed tunneling around. But as we try and extract position measurements, what we are really doing is collapsing the atoms back to the same lattice site. And the more frequently we do the more frequently we extract position measurements from the atoms, the more frequently we collapse the atom back to that lattice site. And so it never actually gets going anywhere. And if it doesn't get going anywhere, it's never going to find a partner. And if it's never going to find a partner, the lattice lifetime, while we are shining more light on the system, but quantum mechanics says, because you are localizing the atoms more and more frequently, you expect less photo-association. Classical physics says photo-associative loss is a given in your system. You shine more light, more photo-associative loss. Quantum mechanics says, no, you're doing position measurements. You shine more light and you're doing more frequent measurements. You're stabilizing the system. You get less photo-associative loss. And so, and what is more or less? What is it compared to? It's comparing two rates. The rate at which we are extracting position information from the system and the rate of intrinsic tunneling. If the tunneling rate is much, much larger than the rate at which we are extracting position measurements, then the fact that we're looking at the system very, very occasionally or very sporadically has no effect on tunneling. So that's this regime. Nothing happens. Okay? We observe the system, nothing happens. Because if we are observing the system very sporadically, at some point we go from this regime to this regime. the rate at which we are measuring the system and thereby localizing it actually is larger than the coherent rate. Then we are localizing the atom repeatedly. And so then the lifetime starts going up.
Good. Is there a background rate at which this photoassociation happens?
There's a very small background rate, yeah.
Okay.
And that comes about just for the fact that we're actually continuously cooling the system.
So if you didn't have that, you'd expect the lifetime to get shorter until you hit the tunneling rate and then get
Exactly.
longer,
So
something like that.
really, if I got rid of that, if I got rid of the position measurements and say what's the background at all, as I go to the, there is a offset here because of that intrinsic cooling rate. And if I go to the zero of that offset, this will actually go way up.
Right. Okay.
Yeah. Good. Make sense? So now I kind of explained this in a kind of a binary fashion. You either measure or you don't.
And also, if you had thermal hopping instead of tunneling, I think.
Then this would, in a sense, just be this is for the ground band.
Right.
And the higher band tunneling just increases at a pretty rapid rate. And I'll come to that in a couple of slides.
Okay.
We understand that as well, but I'll come to that in a couple of slides. But I made this sound like a rather binary thing. You either measure, in which case you localize, or you don't measure and there's coherent hopping. But it's not quite a binary thing because it depends on the strength, and you can see that there's some clear crossover between two behaviors. Short time or weak measurement rates, nothing really happens in lifetime. Larger measurement rates, it starts going up. Then you say, well, I have a huge dynamic range. What happens later on? What happens if I keep cranking this up? And this is this localization idea. And if you actually treat this not in a lattice but in a kind of minimal kind of a system of saying I just have two sites and the atom's going to hop back and forth. And I try to measure the position of the atom and say which site is the atom actually in. Turns out that there's actually a very continuous regime where for very weak measurements the hopping rate is just the Bayer tunneling rate. But as you go to larger, stronger measurements, the hopping is actually suppressed and it becomes a second order perturbative effect. And so the effective hopping rate actually goes as J squared over gamma m, where J is the Bayer tunneling rate and gamma is the rate of measurements. So you can recognize the second order perturbative structure here, which is basically saying that the more frequently I measure this, the more I suppress hopping. But it's a continuous effect. Okay? And this is something called the quantum zeno regime. That for very weak measurements, I expect the measurement to have no effect. And as I go to very strong measurements, I expect this second order perturbative structure where the tunneling rate actually goes as J squared over gamma m, and we see that very clearly. And as we go to very strong measurement rates, we see that the lifetime increases linearly with the measurement rate. And if we go to very strong measurement rates, we see that the loss rate kappa goes quadratically with the beta. So we've gone from no effect to a second order perturbative effect, and this is a classic signature of something called the quantum zeno effect. That by the act of measurement, you actually suppress coherent And then coming back to Pierre's question, there's actually been many papers in the literature, including one by Willis Lamb, which basically say, I'm going to look at this so-called quantum zeno effect in the context of position measurements, and look, there is no such thing. Now, why do they say that? The reason they say that is actually, in a sense, a very good argument, which is to say, look, these atoms are in some kind of a trap. Now I'm trying to do position measurements on it. What am I going to do? What is the side effect? I'm going to impart energy. The more frequently I do position measurements, the more energy I'm going to impart. So what's going to happen? At some point, the atoms are just going to boil out, and they're going to delocalize. Okay? That boiling out competes with the zeno effect. So the very act of position measurements gives the atom energy, and that because of that energy imparted, I'm going to delocalize. So if there is any kind of a zeno effect, at best it's so transient that nobody's ever going to see it. But what have we done? What we have done is to say, no, we are going to extract position measurements, but remember that cycle. Each time we extracted a photon, we brought it back to the ground state. We are removing the energy. So we are saying, no, you don't have to be, you don't have to do that because we have very good cooling techniques. We can extract position measurements, but we can cool the atom back down almost as fast as the rate at which it's advertising its location.
So was the state of the photon that left when you go through that cycle sufficiently resolved in energy momentum that you could image where that atom was in that lattice site?
Yeah, and so that's actually a very good question. So at the end of the day, if you just look at a click, then you say, well, I kind of know where the photon came from. But you could do more than that. You can resolve that photon in terms of its polarization, in terms of its momentum, in terms of its energy really well, and then you can get more and more precise. But all that at the end of the day comes back to the question of what is the wavelength of the photon you're using to image the atom. And the wavelength of the photon you're using to image the atom is commensurate with the lattice spacing. Okay. But not too much more than that, and there's a factor of 1 over 2 pi involved and so on. But in essence, what we're actually doing is each time we hear a click, or each time the atom scatters a photon, we are roughly localizing the atom to about a lattice. If you were to image with, say, a UV photon, then you would localize it even more.
So how many vibration levels do you have in your trap again?
For the shallowest lattices, maybe 4 or 5. Okay. And so basically, in order to be able for us to see this quantum zero effect so clearly, we had to take into account a lot of rates and then find the right parameter space to work in, and then the quantum zero effect actually becomes very apparent. And it's not a transient effect; it's actually a steady state effect. And if indeed we go past this very, very fine region of parameter space, what happens is that we now promote the atom to higher bands. The higher bands tunnel faster. So J is actually higher, and so instead of this linear rise of the lifetime with the measurement rate, you actually start seeing deviations. But if you take into account the right tunneling rates as a function of vibration index, this band is actually the theory that Yogesh did, it matches really well. Okay, so we understand that as well. So now you can say this is some kind of ongoing work. I can skip it if you're running out of time. 10 minutes, okay, good. So you can say, look, this is all great, but you're scattering photons. In order for you to be able to do the position measurements, you're scattering photons. That photon is dumping into some black body radiation. You don't know its polarization and so on and so forth. So in a sense, what you're doing is decoding the system. But that's really not what you want to do. You want to be able to control the lattice gas through measurement back action without actually decoding the system by retaining many body correlations. How do we do that? And one of the things we're working on is to say we can go from a direct measurement, which is the atom scattering photons, to an indirect or a null measurement, which is this scheme here, where I shine light on sites where there are no atoms. Then you say, how is that? Why does that have any measurement back action? It does, because the absence of a click means that you've projected the atom into a subspace of wave functions which have a node at this site. So there is a back action. If you have only 2 sites, this sequence localizes the atom just as much as this sequence. But where is the interaction? How does this atom know that there is some light here? If it's being localized here. And there's actually, I don't know to go into it, ask me after something how this actually works, but there's actually a very, very nice paper by Dickey on saying, is this really a paradox, or does this actually make sense? And it's actually very interesting. This paper came out in '91, and in the acknowledgements, he thanks Victor Weisskopf for a conversation that set this idea in motion that happened sometime in 1947 or so. So that's kind of what we're working on, and this is a very, very nice kind of a scheme, because we can now look at a completely quantum coherent system and change its many-body properties by that of measurement while retaining many-body correlations. So that's actually very nice. So what I've told you about is that measurement back action, and indeed any kind of a reservoir, whether it be quantum or classical, actually is actually a very, very powerful thing, because it can be used to go from to create novel behavior in a many-body system, in a many-body context. And this transition we saw from coherent hopping to diffusive kind of a transport by the act of measurement is actually one example of something called a quantum to classical transition, where now the classicality or the emergent classicality is because of measurement. But you can also use it to you can also use such measurements to create new kinds of physics, like measurement-induced transport, many-body localization, or measurement-induced dynamical phase transitions and so on. And we are approaching this, because of my background, from a very cold atom or bottom-up picture. It's also interesting to say what happens if we go the other way. Go from this is a open quantum system that is more quantum than open. This is an open quantum system that is more open than quantum. So what happens if we take this system, a cavity optomechanical system, which is and make this quantum compatible in the sense that we can now optomechanically cool this system or this mechanical degree of freedom down to the quantum regime and approach the same physics from this side. Do they meet? Which would be the, I think there was that would be a good channel, the tunnel from England and the tunnel from France actually meeting at the same point, or is it screwed up? Do they end up with two channels? Where does this go as opposed to where does this go? That's a very interesting problem, and thankfully in our lab we are in a position, you just have to, if you walk 20 feet away, you get from one lab to the lab that Aditya and Yogesh are working on, and they are going this way. And the question is, where do we actually meet? And so I have 5 more minutes, I think, and so let me just use this context of this measurement-induced or reservoir-induced engineering to create new transitions to go back to the phonons and say here, I'll show you how, even in the classical regime, so I've shown you how measurement or coupling to reservoir changes the behavior of an ultra-cold quantum system. Let me give you a small example of how the reservoir can actually change the behavior of a macroscopic classical system. And I'm going to do this in the context of mechanical nonlinearities. So yesterday I spoke at length about how we have gone through very painstaking efforts to get rid of dissipation, get rid of the coupling to the back, and isolate the mechanical system. So we have a perfect harmonic oscillator, which in a certain sense is the most boring object on the planet. Okay? There's really nothing much going on. What you really want is for these mechanical resonators to be isolated, yet capable of interactions, many multi-mode interactions. And that's good for state detection, back-action evading measurements, nonlinear phononics, transduction, and so on. And you say, well, look, everything's harmonic to second order, but if you drive the resonator hard enough, you're going to get nonlinearities. So what's the big deal? Just tap it really, really hard until things go nonlinear, and that's going to eventually happen. But that's really not what we want, right? What we want is something that is nonlinear, yet still quantum compatible, meaning nonlinearities at the level of 0-point motion. That's really what you want. And in a mechanical resonator, that's actually hard. So classical ducking nonlinearities and so on happen at amplitudes of motion that are 6, 7, 8 orders of magnitude larger than 0-point motion. So that's really not what you want. You can have things which are very, very thin and low mass, like graphene, where the nonlinearities kick in at much smaller amplitudes. But the very source of that nonlinearities, which is intermode couplings, also kill your quality factors. Okay, so it seems like you can either have large classical drives or very, very strong nonlinearities in the presence of strong dissipation. But you want both. You want nonlinearity in the presence of low dissipation. How do you do that? So coming back to the membranes we talked about last time, we said, well, look, the substrate can actually have a huge effect on the dissipation. It can also have a large effect on creating interactions within the membrane that wouldn't have existed in the absence of the substrate. And one particular example is, look, the substrate is also in a sense a plate. It has excitations of its own. And those excitations can actually meet, those excitations are very, very lossy because the substrate is very lossy, it's a reservoir. But those excitations can actually mediate interactions between membrane modes. And in such a case like this, where a substrate excitation is roughly at the sum frequencies of two membrane modes, I have something like, which is exactly a phononic version of a degenerate parametric amplifier. Okay? And this can be very, very strong nonlinearity because the quality factors of these modes are actually extremely large. And we have shown that this system really behaves like a non-degenerate parametric amplifier. We see phase-sensitive amplification, which is basically saying if I have some mode that's being actuated, and I engineer this nonlinearity, then I can have, because of this pump mode, if I drive the system at the pump frequency, I can have correlated production of phonons at the single driver mode. And so I have a mode that's moving around because of some actuation, but I also drive a pump, and that pump is going to create phonons in the signal and dimer modes, which are going to coherently interfere with the actuation. So that can either be constructive interference or gain, or very, very good destructive interference. And now if the actuation is purely because of thermal noise, then I get 2 more thermomechanical squeezing. Okay. Now if I go above threshold, where the rate at which I am putting in energy actually exceeds the rate of dissipation, the system self-oscillates. Now I've gone from a parametric amplifier to a parametric oscillator. Okay? And that's a very nice regime, because now what's actually happening is that the phonons in the signal dimer mode are perfectly correlated. In quantum optics, you say this is intensity difference squeezing. The intensities of the signal dimer mode are correlated at the single photon level. Here they're correlated at a single phonon level. And right in between, coming back to my many-body interest, there's actually something that looks identical to an out of equilibrium or a driven second-order phase transition. Okay. Where the mechanical susceptibility diverges, the system sees critical slowing down. In the experiments that we are doing, because the quality factors are already so high, the equilibration or the thermalization time here can be on the order of 10 to the 5, 10 to the 6 seconds. Okay. And studying this transition in terms of in the context of second order phase transitions around the equilibrium physics is something we are doing right now. So say, to what extent can we extract from this very simple system some insights into the nature of critical phenomena, into the nature of how fluctuations, Markovian or non-Markovian fluctuations, can affect the second or non-classical states by taking them from this regime, which is a disordered regime, to this spontaneously broken symmetry breaking broken phase. And in this regime where the 2 beams or the 2 modes are phonon difference squeezed, we can actually have a very, very nice system for nonlinear quantum metrology or super Heisenberg scaling. This is what is done in quantum optics, for instance, with such optical parametric oscillators, where you drive a crystal at a pump frequency that generates 2 pairs of correlated photons, and you can use one of these to image some very weak object, and use the second as your reference. They both have short noise, but in this case, the short noise is correlated. So if you take the intensity difference, you can actually get sub-short noise imaging. Okay. Now we can actually do the same thing or play the same game with phonons instead of photons. And there are various proposals and various experiments that we are working on right now that are expected to yield super Heisenberg scaling in terms of sensitivity. And this is an example of the 2 signal and dimer modes in the absence of the pump drive. And as you can see, thermomechanical motion, they are uncorrelated. And now we go past the threshold, and you see that they are actually very, very strongly correlated. And because the quality factors are so high, at some point we can create these correlations and then switch the pump off. And now the reservoir is coupling it, but the reservoir is hardly there. So then you say, how long does it take for this highly correlated phonon stream to go into this highly uncorrelated phonon stream? And the answer is 10 seconds.
Is that the breakdown time of the natural line?
Yes, exactly. That gives us ample opportunity to do all kinds of metrology and many-body physics with the system. So this is actually a very, very exciting opportunity, and it's kind of, to me, almost, it's a system that's almost embarrassingly simple compared to the cold atom system. But that's great. Oh, so a quick summary here. Quantum measurements, or in general the reservoir, is not something to be feared. Reservoir engineering can actually give rise to very, very nice, novel many-body properties, can influence the system on at a quantum level in ways that you would not have imagined in the absence of the reservoir. So it's actually, reservoir engineering is actually a very, very strong and powerful concept, both from the point of view of dissipation engineering or interaction, engineering new kinds of interactions, to going to all kinds of novel many-body non-equilibrium properties. I've shown you an example of how we realized a Heisenberg microscope for ultra-cold spins in the lattice, and shown that active position measurements of the back action can actually demonstrate the quantum Zeno effect. I've also shown you very quickly how the same reservoir engineering concept can actually engineer very strong quantum compatible nonlinearities in a low dissipation mechanical oscillator, and that gives its own a whole bunch of very, very exciting opportunities for us. So where does that leave us? Hybrid quantum systems have been motivated, as we've spoken about phonons. Today was all about spins. I'm going to ignore this because there's been enough lectures on gravity optomechanics. So tomorrow I'm going to show you how this can couple to this. through different techniques that we are actually pursuing in our lab. All right, thanks.
Questions?
Are you going to tell us why I don't look and still learn something?
I could do that.
What was the question?
These say interaction-free measurements.
Yeah.
How do you look at something,
Yes,
or how do you not? How do I look here and influence peer? The answer is that peer actually.
Just hold a glass of wine.
That's actually true. So what happens is that the atoms, and this is something we're actually trying to experimentally show in our experiments, is that here it's not, in a sense, really interaction-free. The atoms actually undergo a second order or virtual tunneling process, okay, which looks very much like a super exchange turn. The atoms go here, interact with this beam, and then come back, but do so in a purely AC stark shift or a potential interaction turn sense, but do not actually scatter a photon, or do not spontaneously scatter a photon. So it's something that is a coherent interaction, which looks like a super exchange or a virtual tunneling turn.
So I think of it as that, given the finite tunneling rate, the wave function for the atom actually extends through the entire lattice, right? Those are the eigenstates. for
It's
periodic
completely
potential.
delocalized,
It's
yeah.
delocalized. And so I might have prepared a state where it is localized more or less in one place, but it still has finite probability elsewhere. And so when I do measure it, I am interacting with it there.
Yeah, but in a way that it's tiny, and it's also fundamentally different from this interaction, because this interaction does not involve emitting a spontaneous photon. And that is key for us, because if it emits a spontaneous photon, it decoheres. If this atom were really quantum coherent or prepared in some kind of entangled state with something else, the very act of a single photon emitted destroys that. This, not so much.
So how do you distinguish case B from the case where you have, let's say, no atoms?
Very good. So when you actually look at the effect on the atom.
Okay.
And then the other question also to ask is, well, isn't this really conditional? If you don't know, how do you know that the atom was not there to begin with? Well, it's a conditional process. We shine light. If you don't see a click, we know that if there was an atom nearby, that was indeed, we did extract some. We did extract, the fact that there are atoms and the fact that I tried to measure whether there was an atom in one site has a back action. Okay, because all the other atoms, I projected them into a subspace which have a node at the site I measured.
A node in their wave function?
They node in their wave function.
So you're not actually collapsing the wave function and localizing it that way. You are creating.
You're creating a quantum Zeno subspace of states in the Hilbert space which all have a node at the site you measured. Now that subspace can be many wave functions and they can coherently evolve.
It's like quantum whack-a-mole, right?
Yeah. Yeah, absolutely.
So is there, if in the process where you start in the ground state and then you do that loop, is there some back action into the particle, like in its phase or something like that?
Yeah, but that goes into that phase is completely kind of washed out by the spontaneous emission. And that's why this is this in a sense gives you very similar physics, but without that process.
And how realistic is it for your guys in your laboratory to actually, like, it'd be so cool to see a video of where these atoms are.
Absolutely,
And
and
that's
that's
turn up the light, they get frozen.
absolutely,
Right,
and
that
that is
would
actually Yogesh has a nice fermionic experiment on lithium. These quantum statistics don't matter so much. We are pursuing lithium for other reasons, but importantly, that experiment is compatible with, and we're actually working on single-site resolve imaging in the lattice on that experiment. And at that point, you can actually take these movies very much like Reiner's lab or Emmanuel Bloch's lab have, and you can say, I don't need photo association to probe tunneling. I can actually just look at the atoms and take movies, and that would be a gorgeous thing to do. And that's actually what we're working on right now.
A movie that only a physicist would love.
Yeah, it looks like a bunch of dots randomly moving, but it'll be gorgeous.
Would PRL publish it?
We should ask.
We'll find out.
Yeah, yeah.
So,
Because I think the camera is still on, right? So, yeah.
yes, that's true. So, any more questions?
I would just like to make a comment, and maybe the experts can correct me. But the quantum Zeno effect should essentially also be seen in these mechanical oscillators that you have realized to be near the ground state, in the sense that you just measure it strongly, the localization should be visible. And I don't think there's an experiment out there right now that shows that, look, I'm not limited by the quantum fluctuations at all. I'm in fact at 100 the quantum fluctuation or something like that. That localization should be seen. I don't see why there would be.
The reason I would disagree, I would say I'm your advisor and I'm right, but the reason I disagree with that is that in the mechanical resonator, that would actually correspond very closely to the paper that say Willis Lab had, which is that in trying to localize the atom or the resonator, the quantum entity, to on the order of the 0 point motion, you're actually heating the system up. And that back action, the increase in the noise, the increase in the imprecision upon driving or measuring the system stronger and stronger is precisely what you have seen and Riegel's group have seen and so on.
And precisely what we have avoided.
Yeah, but I'm saying until you get, the point is here, we have avoided that and seen the Zeno effect very clearly because we can simultaneously cool the system at a rate that is much stronger than the rate of measurement. Optomechanics right now, the cooling rates are actually not that strong.
But we have avoided the back action, so I don't see that. That's why I want you guys to say this is wrong. But you
No,
have avoided back action.
I understand we have avoided back action. But are you talking, okay, so what you're really saying is, if you did position measurements on an optomechanical system using back action evasion, and now you probe the system stronger and stronger and stronger, do you see some kind of a Zeno-like effect? Keith, you would be the best.
Yeah, no, I'm just thinking about it. Like, so the realities of our experiment is we barely avoided the quantum back action. We still, the blue points and red points in our curve, with the back action evading points, we still see back action. It's just less than the quantum value. That was kind of the punchline of the paper. It's like, okay, we've gotten the back action below what the cavity back action would be, but we still see a finite amount of heating. So let's say people, smart people, figure out how to do get rid of the losses and these sorts of things, so that you can actually realize back action evasion measurement far, far below. So what state would we have then? We'd have some thermal state we'd start with some thermal state of the two quadratures. Then we start a back action evading measurement. One quadrature gets blown up, heated, and I guess the other one would start, you'd have some state reduction, right? And
I guess what Yogesh is saying is as we get that down to significantly below the 0 point motion, there should be some Zeno-like, I agree. You're right.
Yeah. And maybe one could, but it sounds right. It sounds right. But at this point, where we are in these kinds of measurements, we barely crossed a boundary below the 0 point fluctuation of the cavity effect. So we're not orders of magnitude below where we can localize this thing. So maybe in the future.
Yeah.
So use this political chip wisely.
Yeah, I'm on record saying you're right.
So with that, I think we should thank